Hello, I'm here. Thank you very much. I'm just sharing my screen. How are we doing? Great. Can you see this? Is that working for everyone?
Yes.
Yeah, we can see you, Jenny.
Great. So this is a slightly different talk. I'm not going to be presenting research. I'm going to be talking about a research programme in embodied intelligence by the UK's Advanced Research and Invention Agency, ARIA, which I'm leading. So I imagine many people in the audience won't be familiar with ARIA already, so I'll just start out by giving you a bit of an introduction. We're aiming to be a new kind of agency, certainly for the UK. We are based on the ARPA model in the US. So we're aiming to pursue research and development in underexplored areas that could really change the world. And we have a people first model, starting with the programme directors and working down. We're very multidisciplinary by design. We're aiming to solve problems rather than work in particular disciplines. We fund any kind of organisation, so it could be an academic lab, but it could be a big company, a startup, or even an individual. And we can also fund beyond the UK as well. So our model is that a programme director like myself, when we join ARIA, we first identify an opportunity space, which is an area of science and technology that we believe is both important but underexplored relative to that importance and somehow ripe for exploitation, like now is the time to attack that. And then within the opportunity space, we launch programmes that are focused sets of projects aimed to achieving a particular research goal. We can also fund some opportunity seeds, which are individual projects outside of programmes. And a final piece of jargon, we talk about creators as being the people that we actually fund to do the research and create the breakthroughs. We currently have 7 live opportunity spaces, although we're just about to recruit our new cohort of programme directors, so more will be coming soon. Currently, the opportunity spaces are programmable plants, so synthetic biology applied to plants, scalable neural interfaces, nature computes better, looking at better ways of better compute hardware to run AI algorithms, mathematics for safe AI, aiming to produce formal mathematical verification techniques for AI, and 2 on climate, scoping our planet, improving the quality of data available about climate change, and future-proofing our climate. But the one I'd like to talk to you today about is my opportunity space, which is smarter robot bodies. So this is looking at robotic hardware, the bodies with which robots interact with the world. And within that wider opportunity space of smarter robot bodies, I'm running a programme on robot dexterity, just because dexterity is so vital for everything we would like robots to help us with. So the kind of theory of change here is that robots have been getting more capable over time, but fairly gradually, right? There hasn't really been a step change until quite recently, when suddenly the advances in AI have unlocked tremendous potential in robotics, and there's a lot of excitement and investment in robotics at the moment. So that's great. But my claim is that eventually, or in the fairly near future, roboticists are going to find they're limited by the available hardware that they have to work with, and that's going to prove a hard limit, a ceiling for how good robots can actually get. So in my ARIA programme, I'm aiming to fund new technology, new components for robotics and new approaches to designing robots. Initially, of course, that won't be as good as the more mature technology like DC electric motors and so on, but my hope is that in the future, that technology funded by my programme will mature enough so that it's then in place, enabling robots to carry on improving and do everything we need them to do for us in the future as the world increasingly faces labour shortages. So my background isn't actually robotics. I trained in physics originally, but I've worked for many years in neuroscience, so I've been thinking a lot about biological brains and bodies. And I'm really struck by how much more capable biological bodies are compared to robot bodies. And it's just clear that biological bodies are made out of much more advanced components than are available to roboticists. So that immediately suggests a starting point for my programme. We should aim to improve the components available to roboticists, so better actuators, better sensors, and so on. And the other point that struck me was that in robotics, there tends to be this divide whereby a mechanical engineer will design a robot body and then kind of hand it over to a computer scientist to go, okay, figure out a good control policy to animate this thing and to make it do what we want. So there's this separation between brain and body, which of course I don't need to convince this audience of, is very alien to nature. So in biology, neural control systems have absolutely co-evolved, deeply integrated with bodies, and that enables nature to exploit the material intelligence of the body in a way that I think is neglected a lot in robotics at the moment. So another part of my program is aiming to replicate that co-evolution through the advanced physics-based simulation techniques that are just now becoming available. It's obviously been tried in the past, but I think now it's really ripe for making progress. So just to fill you in on where we are at the moment, we launched our call last year. We received nearly 200 concept papers, 64 full proposals, and we've selected 25 projects to fund. Most have already started. 17 have already been announced on our website, so those are the ones I can talk about today. We are funding a lot of work on actuation technologies because I think this is really a key bottleneck in conventional robotics. There are all the available technologies have their own problems, whether that's hydraulics or pneumatics or DC electric motors. So we're aiming to come back to some technologies that have been explored but never really got ready for prime time yet. So Hazel actuators, dielectric elastomers, looking at new approaches to electromagnetic actuators, and new approaches to pneumatic artificial muscles as well. One I just want to pull out, because I haven't got time to talk about all of them, I thought I would pull out Sanctera, who are working on microhydraulic actuators. And these are some figures from their recent Science Robotics papers. It's a really interesting approach because they're looking at making an actuator, essentially a motor, which is driven basically by surface tension. So they have two planes, one with electrodes at the bottom here, one with a plate on top that's got grooves in it in which sit little water droplets. So you've got this array of water droplets linking the two planes. When you turn the electrodes on, it changes the nature of the contact between the water droplet and the surface in such a way that it pulls the droplet to the right in this case, and then the entire top plane moves to the right as well. And you can imagine that by cycling through how you turn the electrodes on and off, you can step these water droplets across the electrode array. And I've got a little video from their supplementary materials showing how that works. And you can see this is incredibly fine scale. So 4 of these electrodes occupy 48 micrometers. So this is exciting because it gives the opportunity, or if they can overcome the technical challenges, they'll be able to build really tiny motors, both linear and rotational. And for robot dexterity, the particular excitement is that potentially these would be small enough to go directly in the finger joints. So most robot dexterous hands at the moment are controlled by tendons, very much like human hands, where we have lots of muscles in our forearms that move our fingers. But this would open up a completely different design approach where you could put little actuators directly in the finger joints. And the great thing about electrowetting is that it actually becomes more powerful as you scale everything down, whereas conventional inductive electric motors become less and less efficient as you make them smaller. So basically your motor turns into a heater, and that's why this approach hasn't been viable at the moment, but could be at the end of the programme. Great. Trying to advance my slide here. Come on. Are you seeing? Oh, I've gone to the end of the talk. Sorry. Right. So we're also funding work on sensor technologies. So I think a key problem with robots at the moment is they're largely working without any sense of touch. So typically have an incredibly crude sense of touch, maybe a force torque sensor at the wrist, maybe some tactile sensing in the fingertips. If they're lucky, most commercial robots are working purely through vision, basically because cameras are cheap and ubiquitous. So we're funding quite a lot of work on different sensor technologies to try and sense things like pressure, temperature, proprioception, so how a hand is moving. And I'm excited about these projects here. And then finally, I mentioned the co-design approach, where we're trying to evolve the hardware along with the control. So we're funding a whole bunch of projects in that, not all which we've yet announced to try and attack the problem, including vSim technology, which is a startup using really accelerated simulation. So we're excited about what they can offer because they're going to speed up simulation to such an extent that it becomes feasible to explore this vast parameter space. Min Pan at the University of Bath is going to work with us on improving the way we can model and understand soft materials. We've got Morpho AI, which is a US startup, helping us develop AI tools for CAD design and so on. So these different groups are working very closely together to attack different aspects of this block diagram. So how you define the tasks that you want your robot to perform, and you can make available digital twins of the components that it could have available to it. Obviously, robots don't have access to biological muscle and nerve and so on because we don't know how to make those, but they will have access to novel sensors and actuators, which we can represent in simulation even before we can build them. And then we're going to go through this loop where you try and optimize the design of the robot body and the control policy. And then we know there's going to be a sim to real gap. So we will test it out by rapid prototyping, figure out where the simulation isn't quite matching up with reality, go through that loop again, but then hopefully at the end up with a CAD design and bill of materials for a novel manipulator in our case, and the control policies to enable it to perform the tasks we need it to. Finally, we've got a couple of projects where we're looking at funding people to work on entire manipulators. So Arthur Hand is a brand new startup in London, and they're aiming to prototype dual-armed robotic hands equipped with tactile sensing. We're also excited to be working with the National Composite Centre, both because they have expertise in how to make advanced materials, but also because they have some really interesting use cases for robotics. So they're explaining to me how really advanced carbon fibre components for aircraft to a very large extent have to be made still by hand. So there are technicians manually laying up the composite material because at the moment it's just too dexterous a task to be done by robots. So they're interested in working with us to see if our creators can help that or them automate that task for the first time. All of those projects that I've spoken about, you can find on our website. I've put the QR code here. We do also have 8 other projects yet to be announced, so keep an eye on our website for them to go live soon. That's all I wanted to say in my talk. I'll be very happy to answer any questions either now or in the panel discussion as appropriate. Thank you.
Yes, thank you very much. You have a question in the chat.
Great. Can't immediately see the chat. Would you mind reading it out for me? Oh, there we go. Chat.
Sorry, I guess like the Q&A are like during the discussion.
Right.
It's not right now, yeah.
So I'm seeing a question about ground control policies into the body. Will this be a valid objective for opportunity seats? So this is someone who's clearly familiar with the programme. We are intending to launch another call for opportunity seeds later in the year, still trying to figure out exactly when. I think, to be honest, this is not going to be within scope for opportunity seeds because we're already addressing that in the programme. So I feel like I've got that covered, and I'd like to use opportunity seeds to explore ideas that are outside the scope of the programme.
Yes, thank you.
Great.
We have one more.
So are we going to have further calls? Essentially, no. ARIA programs are basically, one-off things that run. We will have future programs, so definitely keep an eye on the website. You can sign up for updates, but I can't at this stage say exactly what they will be on. They may not be on dexterous robotics, for example. Our model is that we have one-off programs, and then a new program director comes in and decides what's most needed at that time. And we're a very small agency, so we don't, we're not aiming to replace UKI or anything like that. We're exploring increasing the variance, basically, of UK science funding. Absolutely, you can apply from overseas. That's not a problem at all. We look at UK. The benefit to the UK is one of our assessment criteria. So, for example, some of our creators are setting up offices in the UK for the first time, or recruiting in the UK, or making the components that they develop available to UK creators to use. So we will look at that, but being outside the UK is fine. Many of our creators are outside the UK. Great, thank you, Kay.
Okay, thank you very much.